All right, we're back with the Codebook explorations, and we're almost done. Maybe today we can finish the introductory sessions. So now we're doing some multi-qubit entangling and separable discussions. Basically, entangled states are not separable. And so you can see, for example, over here, the canonical sort of Bell state or EPR state is entangled. And so one way to do that is controlled operations. So the first thing we have to do is write a circuit that implements a C0 between two gates. So we will simply do .C0, and then we specify the control, which is 0, and the target, which is 1. And this should eventually submit. Of course, I could be misunderstanding this problem. Oh, we have to run it with various inputs to fill out our table. I see we actually just have to fill out this truth table. Let's see if that is correct. Maybe we are supposed to do this out. So we have this 0, 0, 0, 1, 1, 0, and 1, 1. And we can see what the output is. I don't understand. Oh, this is supposed to be the binary representation. Whoopsies. That's my bad. Okay, the truth table is replace the bit strings values with the correct one. Oh, that's right. I mistyped that one. It's like, what's going on here? This should be right, but because this is, by the way, how you make the state over here, right here, which is clearly not separable, entangled. Let's see if I actually have to do anything or if it just, yeah, okay. So we first apply a Hadamard gate, and then we apply a C0. That's good. Yeah, Bell state, like I said, controlled U operation, controlled rotations. So now we want to do the circuit above. So we want to do CRX theta wires equals 0, 1. Then we want to do CRY B wires equal 1, 2. And then we want to do CRZ omega wires equal 2, 0. And then we want to return the probabilities. All right, that one was not bad. Now we're doing more controlled operations and multi-controlled operations. So now we want to complete the function imposter CZ to, so we want to do CZ here, CZ. I don't really know what these, I don't know what the angles, oh, prepare states. Oh, that's some function we don't have access to, I guess. So we know that controlled Z operation is an X gate on the second qubit, conditional on the first. So we can simply convert this basis into the X basis, and then the X gate will act differently, right? So if we Hadamard this, we do a basis change, and then we can just do CX in this basis, and then undo our basis change, and we will get the result because we have this Hadamard, right? It converts it to the X basis, do our operation, then reconvert it to the Z basis or standard or the working basis. Oh, right. There's no CX. Seems like it should be aliased as that, but that's my most common complaint. All right, and that's exactly right. So now we have the swap, which just exchanges the states. Swap can be done via real swap. I assume it's just swap. I don't know if that's actually what it's called. And it's known that we can simply apply 3 C0 gates to mimic or decompose a swap. That's just a known sort of thing here that is a common identity that you'll see. So now we have Tafali, which is a common gate. It's a 3 qubit, also called the CCX gate, controlled not gate. And this controlled swap is also called the Fredkin gate, named for whoever Fredkin was. So what we want to do is do a swap. So we want to decompose a controlled swap gate into a sequence of from a sequence of Tafalis. So I'm not sure the exact identity necessary for this. So let me think about I'm just trying to think about what the best way to do this. I'm sure it's a similar sort of idea as this one up here. I see. So what we're doing is a controlled operation here. So each of these are going to be controlled by the 0 qubit. So we want to do the same as above. This is my guess. You know, I could be it's gonna be a little awkward if this is completely wrong. But let me just look up how they do Tafali. Somewhere. Oh, it is just Tafali. Okay. We have our Tafali gate, and we have our wires, which is 0, 1, 2. So we're going to do 3 Tafali gates. And we're just going to keep the 0, 1 the same. And then we're going to swap these two. What do you know? It's the same idea, right? Because this is the gate we're doing. We just add a control at the top. So we just add a control to each of these sort of positions. I don't know if that's universally true, but it kind of seems like it might be. All right, now we can have an arbitrary sort of multi-controlled X gate. We can also specify, so this is controlled when it's off, this is controlled when it's on. So if it's in the 0 or 1 state, if it's in the 0 state here, then it'll be true. If it's in a 1 state here, then it'll be true. So we want to do this multi-controlled X. This is very control wires equal 0, 1, 2, 3. And then we have our, actually this is just 0, 1, 2. And then we have we have 4 wires. Not all of them are controlled. And then we have control values, which is 0, 0, 1. All right, but first we have to do our atom arts on. And submit that. Did not find wires 0. Well, maybe there does need to be a 3. Let me just put a 1 down here. Did not find some wires. Oh, okay. These are the wires. That's so weird. You just specify the controlled wires. You don't say anything about the target. I don't understand. Oh, the target wires is not, I thought this was the total number of wires, but that's actually the target of the multi-controlled X. I feel like there should be like target wires or something, but it's just wires. All right. So now we have a 3 controlled NOT. And now we want to implement this gate using defaulties. So we're going to need an extra one. Let's see if we need to uncompute this. So we want to first do we can do these two and then these two. So we'll do QML default wires equals 0, 1, 3. I'll just do 1, 2, 3, and then this will tell us if both of these are true, then this will be in the original state, in the 0 state. If either of these are false, it'll be in the 1 state. So we need to do another one, which will be 0, 2, 3. So now if all 3 of these are true, so every pair is true, then we have, so it goes from 0 to 1, 1 to 0, back to 1. Whereas if any of these are false, if C, let's just consider C is false, but these two are true, or this is 0 and these are 1. Oh, right. So we're using our auxiliary. This is my bad. So we want to do this is onto the auxiliary. 0, 1, 2, 3, 4. We should use. So then these two are true. So then we want to use a third Tafali to the fourth qubit, the last one, and we want to say, okay, if these two are true, and these two are true, and then we'll have a we need to do X on this first one. So then this will be in the one state if both of them are true, or if both of them are false. So then we'll do a controlled operation using any of them. In this case, we'll just do 0, 3, 4. We might have to undo our operations. Yeah, because we want to uncompute on these wires, we're going to. Is this not right? Let's see. I should. Well, let me just check something. What I need to know what ordering this system uses. So this is the 1, 1, 1, and we want it to be in. So it's 1, 1, 2, 3, 4, 5 qubits. So there's 32 possible states, and so 16 plus 8 plus 4 is 28. So that means there's going to be 4 left. So it's 1, 2, 3, 4, 28, 28, 29, 30, 31. Yeah, so this is the initial state. And we want it to shift to, this should also be a 1. So it should shift up by 1. So we want it to be here when we do our operation. Yeah, so this will shift it up 2. Then this will make it shift it back down. This will shift it back up. And then we want to, now this should move it all the way to the end. And then we want to undo that. And that should be the desired state increased by 1. We can also uncompute. Oh, are we not supposed to use any poly X's? Is that the problem? Only to follies. Oh, I see. I think that is the problem, is that we're not supposed to use a poly X gate. I think I can just, let me comment these out. If we just add an extra one of them in here, so now we have 0 and 2, this should work. And then we want to uncompute it, of course. So I'm just uncomputing them. Okay, well, your gates are not applied to the correct wires. Well, I really think that they are, actually, because that's the exact state we want. 1, 1, 1, 0, 1. 1 times 1 times 1 is 1. So that's going to be 2, right? Because this is the 2 place of the binary. And it only uses to folly gates. So I actually do think it's I actually do think that this is correct. I feel like it has some oh, oopsies, I didn't want to do this twice. Yeah, I don't think this is wrong. And I mean, it's not wrong. It generates the right output. I think intuitively it's right. But let me see. CCCX following. This might just be yeah, this is just multi-control. Okay, so yeah, we have this. Yeah, I see. What we can do is basically this. We do control, control here. Does it want it more efficient? I don't think with only one ancillary qubit that that's possible. I'm confused right now as to what's going on. Why? This seems like it should be right. I'm getting the right results, I feel like. But Codebook. This is I13. I do not know why this is not correct. Because this technique here that I'm looking at would use 2 control or 2 ancillary bits instead of just 1, which is not what I want. Why does this happen every time? Last time this happened, literally what I had to do was I had it exactly right. For some reason, the adjoint function wasn't working. So I feel like something's going on here because this is the right output that we should be getting. Here, I'll check what happens if it's not the right output. Actually, that's going to be, I'll do it this way. So then we'll have 8, 4, 0, 0. So it's 12. So it's going to be 0, 1, or 1, 2, 3. No, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Exactly right. So this seems like it's the right way. I mean, it got mad at me there because I commented down a polyx, but I do not see how this is incorrect. Just seeing if anyone else has. Oh, there's hints. Let's look at those. Only 3. Okay. That's why, because it wants me to be as efficient as possible. I bet that's why. Oh, I see what they want us to do. They want us to do this. They want us to do 0. They want us to do this. I'm pretty sure. 2, 3, 4, and then recopy this. Okay, that's right. Okay, but literally, my code also worked. Just because it wasn't exactly what you wanted doesn't mean it's not right. Yeah, this is what's going on here. Okay, I guess that's it. That took longer than expected, but that's all for now.